Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the last video, I worked through the design of a pi configuration impedance matching circuit the easy way using a Smith chart. Now, if you missed that one, I've provided a link in the description and, well, up in the corner for you here. You can also do this with some more work using math, and that is what this video is all about. I am going to walk through the process of designing a pi configuration circuit that will provide a match between the same two impedances that I worked with in the last video, only this time I'm going to be using the equations. Like the last video, I'm going to be repeating some things that I said in the videos on designing the L-type A and B matching networks using math, so this can be a self-contained video. Now, if you've watched either one of those videos, then, well, there'll be a little bit of review in here, and that isn't necessarily a bad thing. I will put a link to a zip file in the description, which contains the formula sheet and the octave.m file for this demonstration. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. We begin, as always, by defining our objectives. Well, our objectives are quite simple. The overall circuit looks like this. We have a source impedance of 100 plus J200. We have a load impedance of 50 plus J50. We're going to operate at a frequency of 50 megahertz. Now, we have to prepare our circuit for the mathematical process. To prepare our circuit for the equations, we begin by getting the source and load impedances in the same configuration as the matching networks. If the matching network's reactance is in series, then we must have the associated source or load impedances expressed as a series combination of resistance and reactance. This means impedance is equal to R plus Jx, which is the form which we normally express impedances in. If the matching network's reactance is in parallel, then we must have the associated source or load impedance expressed as a parallel combination of resistance and reactance. This means impedance is equal to resistance in parallel with reactance. For a more complete explanation of the parallel equivalence, I will point you to my video on the subject. I've placed a link in the description and up in the corner for you. The transformation from series to parallel is a relatively easy one to make. Both the input side and the output side of the pi configuration are parallel entities. So we have to transform the series form expression of our source and load impedances into their parallel forms. With the series expression of impedance equal to the series resistance plus J times the series reactance, the parallel equivalence may be found with these two equations. The equivalent parallel resistance, R parallel, is equal to the series resistance squared plus the series reactance squared divided by the series resistance. And the equivalent parallel reactance is equal to the series resistance squared plus the series reactance squared divided by the series reactance. Thus, our impedance Z series, which is expressed in terms of a series resistance and reactance, is now expressed in terms of a parallel combination of a resistance, R parallel, with a reactance, X parallel. Our source impedance is 100 plus J200, so our series is equal to 100 and X series is equal to 200. So that gives us an equivalent parallel resistance is equal to 100 squared plus 200 squared divided by 100, which gives us 500. The parallel equivalent reactance is equal to 100 squared plus 200 squared divided by 200, which gives us 250. Our source impedance, as expressed in terms of parallel components, is a resistance of 500 ohms in parallel with a reactance of J250. Now, we have to do the same thing with the load impedance. And this gives us a load impedance, as expressed in terms of parallel components, of a resistance of 100 ohms in parallel with a reactance of J100. So, our next step is to begin putting stuff into our equations. Well, the equations we're going to use refer to an R1 and an R2. R1 is the real part of the impedance associated with the input side of the matching network. In this case, this is the parallel equivalent resistance of our source impedance, and we calculated the parallel equivalent resistance to be 500 ohms. Therefore, R1 is equal to 500 ohms. R2 is the real part of the impedance associated with the output side of the matching network. Like the source side, this is the parallel equivalent resistance of our load impedance, which we calculated to be 100 ohms. Therefore, R2 is equal to 100 ohms. We will be calculating X1, X2, and X3 with our equations. But what do these refer to? Well, X1 is the reactance of the parallel combination of the reactive portion of the equivalent parallel expression of the source impedance and the input parallel component XA. X2 is simply the reactance of the single series component which exists between the input and output. X3 is the reactance of the parallel combination of the reactive portion of the equivalent parallel expression of the load impedance and the output parallel component XC. Now that we know what we're going to be doing and with what, let's do the math. Well, the first step in doing the math is to determine the phase angle. And so you ask, what's this business with phase angle all about? And you know, the amazing thing is that people talk about it, but never actually say what it is. Well, it has to do with the phase of the output relative to the input. Okay, so what do I mean by the input signal in this context? Well, in this example, we have a signal source which has an output impedance of 100 plus J200. This signal source consists of a perfect voltage source which has an output impedance of 0 ohms and a phase of 0 degrees, followed by a series resistance of 100 ohms and a series inductive reactance of 200 ohms. This input signal is the output of this perfect voltage source. The phase then includes the phase shift of the output impedance of our source and the effects of the reactances associated with the impedance matching network terminated in the load impedance. Unlike L configuration matching networks, we get to define the phase angle. According to the impedance matching book that I got the equations for X1, X2, and X3 from, we can choose any phase angle from minus 180 to plus 180 degrees. Well, being curious, I created an Excel spreadsheet which explores the effects of the choice of phase angle on the solution to this particular impedance matching application. If you are interested in that spreadsheet, there is a link to the zip file which contains the Excel spreadsheet down in the description. Based on what I saw in my spreadsheet, I'm going to choose a phase angle of 60 degrees for this particular application. So, beta equals 60 degrees or 1.0472 radians. Now that we have the phase angle, we can move on to calculating X1, X2, and X3. And here is the equation for X1. We get that X1 is equal to R1 times R2 times the sine of our phase angle beta divided by R2 times the cosine of our phase angle beta minus the square root of the quantity R1 times R2. And we know that R1 is equal to 500, R2 is equal to 100, the phase angle beta is equal to 60 degrees. Putting all these values in our equation, we have that x1 equals 500 times 100 times the sine of 60 divided by 100 times the cosine of 60 minus the square root of the quantity 500 times 100, which gives us a reactance for x1 of minus 249.42. But this is the parallel combination of XA, our input component, and the source's parallel equivalent reactance. We have to disentangle these to arrive at a value for XA. To do this, we use this equation. The source's parallel equivalent reactance times X1 divided by the quantity the source's parallel equivalent reactance minus X1. And we know that the source's parallel equivalent reactance is 250. So XA is going to be equal to 250 times negative 249.42 divided by 250 minus a negative 249.42, which gives us XA equal to minus 124.86. Now, we know it is a capacitor because the reactance is negative. Therefore, we use this formula to calculate the capacitance in picofarads. Minus 1 times 10 to the 12th, all divided by 2 times pi times the frequency in hertz times the capacitive reactance. And as before, our operating frequency is 50 megahertz, and we just calculated XA to be minus 124.86. That gives us the value of C1 is equal to minus 1 times 10 to the 12th divided by 2 times pi times 50 megahertz times a negative 124.86, which gives us a capacitance value of 25.49 picofarads. And this is almost exactly what we got with the Smith chart. Now, on to the next component. Well, the good news is that X2 is also XB, the series component in the middle of the pi configuration. Here is the equation for X2. We have R1 times R2 times the sine of the phase angle beta divided by the square root of the quantity R1 times R2. We know the value of R1 is 500, R2 is 100, and the phase angle beta is 60 degrees. So X2 equals 500 times 100 times the sine of 60 degrees divided by the square root of the quantity 500 times 100, which works out that X2 equals XB is equal to 193.65. But what is the value of this component? Well, we know it's an inductor because its reactance is positive. So we use this formula to calculate its value in nanohenries. 1 times 10 to the 9th times the inductive reactance divided by 2 times pi times the frequency in hertz. And we know the inductive reactance, XB, is 193.65, and we know the operating frequency is 50 megahertz. So that gives us that L1 is equal to 1 times 10 to the 9th times 193.65 divided by 2 times pi times 50 megahertz, yielding a value of 616.4 nanohenries. Now, when we use the Smith chart, we arrived at a value of 636.6 nanohenries, and we're not too far different. Now, we can move on to the next and final component of our pi configuration impedance matching network. And here's the equation for X3. We have R1 times R2 times the sine of the phase angle beta divided by R1 times the cosine of the phase angle beta minus the square root of the quantity R1 times R2. And we know, as before, R1 is 500, R2 is 100, and our phase angle beta is 60. Putting all these values into our equation for x3, we get that x3 is equal to 500 times 100 times the sine of 60 divided by 500 times the cosine of 60 minus the square root of the quantity 500 times 100, which gives us a value of x3 of 1,640.62. But this is the parallel combination of XC, our output component, and the load's parallel equivalent reactance. We have to disentangle these like before to arrive at a value for XC. And we use this equation to do this. The load's parallel equivalent reactance times X3 divided by the quantity, the load's parallel equivalent reactance minus X3. And we know that the load's parallel equivalent reactance is 100. So XC is equal to 100 times 1,640.62 divided by 100 minus 1,640.62, which gives us that XC is equal to minus 106.49. And we know it's a capacitor because the reactance is negative. Therefore, we use this formula to calculate the capacitance in picofarads. C2 is equal to minus 1 times 10 to the 12th divided by 2 times pi times the frequency in hertz times the capacitive reactance XC. And as before, our operating frequency is 50 megahertz, and we just calculated the capacitive reactance XC to be minus 106.49, which gives us that C2 is equal to minus 1 times 10 to the 12th divided by 2 times pi times 50 megahertz times a negative 106.49, which gives us a capacitance value for C2 of 29.89 picofarads. Now, we got a value of 31.83 picofarads using the Smith chart. What this tells me is that I chose a phase angle for this exercise with the math that is pretty close to the one implied by our path around the Smith chart. And this got me thinking, how close? So using my spreadsheet, I discovered that the phase value associated with the values achieved using the Smith chart was 63.435 degrees, or, well, thereabouts. Cool. Now, I'm going to move on to the final check. I'm going to calculate the input and output impedance of this matching circuit. Now, the overall circuit looks like this from an impedance perspective. The first thing that we're going to do is to calculate the input impedance, and this assumes that the output is terminated with the load impedance of 50 plus J50. So it looks like this. Now, when we first look at this, it could feel like it's really complicated. How are you going to do this, all these things here? But it really isn't if we just break it down a little at a time. Now, when I look at things like this, I look for combinations of components that I can find the equivalent impedance of. And the first thing that I see looking at this one is that the load impedance is in parallel with the output capacitor whose reactance is XC. I'm going to call this combination ZOE. So let's do this first. ZOE is equal to Z load times JXC divided by Z load plus JXC. And we know the load impedance is 50 plus J50, and XC is a negative 106.49. So we have 50 plus J50 times a negative J106.49 divided by 50 plus J50 plus a negative J106.49. Using OCTAVE to do the math, we get that ZOE is equal to 99.63 plus J 6.0719. Okay, so now let's look back at our schematic. And we can see that this impedance that we just calculated is in series with the inductor whose reactance is XB. I'm going to call this combination Zm. So Zm is equal to ZOE plus JXB. And we know that ZOE is equal to 99.63 plus J 6.0719. And XB is equal to 193.65. So Zm is equal to 99.63 plus J 6.0719 plus J 193.65, which gives us that Zm is equal to 99.63 plus J 199.722. We're making progress, but we're not done yet. Let's go back to our schematic one more time, and I can see that Zm is in parallel with our input capacitor whose reactance is XA. This parallel combination is the input impedance of our matching network. So Zn, our input impedance, is equal to Zm times JXA divided by Zm plus JXA. And Zm is equal to 99.63 plus J199.722, and XA is equal to a negative 124.86, which means that our input impedance is equal to 99.63 plus J199.722 times a negative J124.86, all divided by 99.63 plus J199.722 plus a negative J124.86. And again, using OCTAVE to do the complex math, this works out to be an input impedance of 100 minus J200. And this is the complex conjugate of the source impedance of 100 plus J200. So we are right on. Next, we're going to check the output impedance. And finally, we're going to turn our attention to the output impedance. Now, this assumes that the input is terminated with the source impedance of 100 plus J200. Now, I eliminated the voltage source at the input, replacing it with a wire because its output impedance is 0 ohms. But like before, this can be a little bit intimidating and look a bit complicated, but not really. We can break this down into smaller pieces, take it a little bit at a time. And so the first thing that I see when I look at this is that the source impedance is in parallel with the input capacitor whose reactance is XA. I will call this combination ZIE. So we have ZIE is equal to Z source times JXA divided by Z source plus JXA, and our source impedance is 100 plus J200, and XA is a negative 124.86. And that gives us that ZIE is equal to 100 plus J200 times a negative J124.86 divided by 100 plus J200 plus a negative J124.86. And using OCTAVE to do the math, I get that ZIE is equal to 99.642 minus J199.731. Now, looking back at our schematic, we can see that this impedance is in series with the inductor whose reactance is XB. I'm going to call this combination Zn. Zn is equal to ZIE plus JXB. And with ZIE equal to 99.642 minus J199.731, and XB equal to a plus 193.65, that gives us that Zn is equal to 99.642 minus J199.731 plus J193.65. And as before, I'm using Octave to do the math. Zn is equal to 99.642 minus J6.081. Now, we're not done yet. We got to go back to our schematic one more time. I can see that this impedance is in parallel with the output capacitor whose reactance is XC. This parallel combination is the output impedance of our matching network. So Z out is equal to Zn times JXC divided by Zn plus JXC. And with Zn equal to 99.642 minus J6.081, and XC is equal to a negative 106.49, that gives us that our output impedance is equal to 99.642 minus J6.081 times a negative J106.49, all divided by 99.642 minus 6.081 plus a negative J106.49. And as always, I do the complex math using Octave to arrive at an output impedance of 50 minus J50. This is the complex conjugate of the load impedance of 50 plus J50, so we are totally, absolutely, positively, unequivocally good to go. Well, as you can see, the process of designing a pi configuration impedance matching network using the equations is not as easy as doing it with the Smith chart. Now, if you mastered the Smith chart version and this one, then you now have two tools in your belt for designing a pi configuration impedance matching network. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, Toodle-Oots.